Okay, now tell me whether if you can see my screen. Okay, thank you. So let's start now. So last class, what we are last class what we are reading, that measurement of inductance by means of bridge circuit. So few bridges we read. So Anderson bridge also we read. Now quickly we'll go through again and then move to another bridge, so that there are various methods of measuring that inductance. So here it is the Anderson bridge. You see that in Anderson bridge, instead of there are four arms, fine, but in with that, after that, with the detector, you see there is another resistance is attached and it is balanced with the capacitance. So if you see the arm AB, there are inductance L1 and the resistance R1 associated with it, and small R1 is the another resistance which can be varied. So L1 R1 is the inductance parameter, where L1 is the inductance and R1 is the resistance of the inductance. Small R1 is the um, another resistance which could be varied. In AC arm, you see there is another fixed resistance R2. In BC arm, there is another fixed resistance R3. In ED arm, you see there is a capacitance which is fixed. This is important. Earlier circuit, we see that the capacitance is not fixed, it is varying, and you know that variable capacitance, which is whose value should be precisely known, is very costly. So instead of that, we use here a fixed capacitance, and there is another resistance small r which could be varied, and there is another resistance R4 in the fourth arm. So if you see that here we could vary the two resistance only, small r1 and small r, capacitance will not be varied, it is fixed. And B shows the phasor diagram. Now if you see at the balance condition I2, what is the I2? This one is the I2. In the balance condition, you see the I2 will be equals to IC plus I4. So I2 will come here, it will divide into IC and I4 and IC will go through the capacitance because no current will pass through the detector. So I2 will be equals to summation of I4 and IC. This is another equation, and you see that VBD equals to VED. Where is BD? This is BD, and this will be equals to ED because there is no current passing through the detector, and the potential at B and potential at E will be same. So the potential drop at BD will be equals to ED. That's what it is written, and I1 R3 equals to this is given. And you know that the IC will be equals to current passing through the capacitor, and that is if that is the J omega I1 R3 C. Okay, because VBD equals to VAD. Now another balance condition could be achieved. At balance condition, VAB will be equals to VAC plus VCE. So VAB will be equals to VAC plus VCE. So here the current potential drop on the AB will be equals to potential drop I2 R2 plus IC small r. So that's what it is written. I1 small r1 capital R1 J omega L1 equals to I2 RC R2 plus ICR. So if you see that again another condition, VCD will be equals to VCE plus VED. VCD will be equals to VCE plus ED. That is very clear. So I4 R4 will be ICR plus here J omega C. That is what we are written. So if you see all these conditions, they are written together, and then a little manipulation, ultimately at equating real and imaginary part, we get capital R1 will be equals to R2, R3, R4 minus R1. What is capital R1? Capital R1 is the inductance resistance of the inductance. As you know, if you want to make a inductance, some resistance will be coming because you will be winding a coil to make the inductance. So that resistance measurement is also important, and the measurement of inductance will be also important. When you give an inductance to anybody, so you have to mention the value of the inductance as well as the resistance with it. So R1 is the resistance of the inductance which is to be measured, and you see the expression of L1, which is C R3 R4 small r R2 plus R4 plus R2 R4. So if you see this expression here also, everything is known, R2, R3, R4, C, everything is known. So L1 could be calculated. So now the advantage of the Anderson bridge over the Maxwell bridge is that in Maxwell bridge we need a variable valid capacitance, but in Anderson bridge we need a fixed value capacitance, and the cost of the bridge is reduced, the accuracy of the bridge is increased. Okay, so but you see that this is achieved in the expense of connection complexity, because you see that connection complexity is little bit more, because there are two extra arms which where the circuit components are connected, and achieving balance condition could be little bit tedious. So this is all about the Anderson bridge. Now we'll go another bridge, Owen bridge. Now let's see if you have anything. Okay, nothing is there. Hope you could understand. So now let's go through the Owen bridge. So if you see the Owen bridge, it consists of four arms. There is no extra arms. And if you see that the first arm is the inductance L1 and its own resistance R1, which is associated with it. And there is in BD there is another resistance R3, and in AC there are two components. One is the resistance, which is can be varied, and another is variable capacitance again. And in the fourth term, you see there is another capacitance only. So B is the phasor diagram. You see that I2 and I1 will be 90-degree apart, and accordingly you can draw it. So now if you see the balance condition what we could write, R1 plus j omega L1, here you see this one, R1 plus j omega L1 by R3, R3 is here, will be equals to R2 plus j 1 by j omega C2. Here this is R2 plus 1 by j omega C2 will be equals to by 1 by j omega C4. It is the fourth arm. So if you multiply it with the two sides and then going simplification with the imaginary part equating as well as the real part equating, you will get R1 will be equals to R3 C4 by C2, and you will get L1 will be equals to R2 R3 C4. You will get L1 equals to R2 R3 C4. So here you see again R1 can be calculated, and by if you know the R3, C4 and C2, and L1 could also be calculated. But here you see that the C2 is a variable capacitance, so you need to know the value of variable capacitance once it is balance condition is achieved. So it is possible for two independent capacitance C2 and C4 and R2 to obtain a balance condition of the Wien bridge. The balance equations are also quite simple, and it could be achieved very easily. This, however, comes with the additional cost of the variable capacitance. Again, repeatedly, I am saying that when capacitance will be varying, and we need to know the value of the varying capacitance, because you see C2 is here, so the cost will be associated with it. It will be more costly. Okay, so now let's see a problem or numericals. Let's solve it. So you see that the arm coil AB, it will be a choke coil L1 with associated resistance small r1. Arm BC will be non-inductive resistance. So this one like this. So our AB is the L1 and small r1 associated with it, and this one you just see that these are the four arms. So one arm will be L1 associated with smaller one. So and BC arm will be R3 associated with, and then AD arm will be R2. Like এইটা লাগিয়ে দেন। So and the fourth arm will be R4, capital R4, C4 and small r4. So you see there are four arms, and so this is mentioned here that arm AB, arm BC, arm CD, and arm DA. So bridge is supplied with the 450 hertz volt. So here is the voltage supply, it is 450 hertz. And you see that AC is a terminal AC is the detector connected between the BD. Balance is achieved by the following condition: when R2 is 2400 ohm, R3 is 600 ohm, C4 is zero point 0.3 microfarad, and R4 is 55.4 ohm. Series resistance of the capacitor is zero point 0.5 ohm. Calculate the resistance and the inductance of the choke coil. So all the components are given, and this is the detector. The input frequency is also given, and you need to calculate. You need to calculate the L1 and R1. So here you see it is written R2 is 2400 ohm, R3 is 600 ohm, C4 is the zero point 0.3 microfarad mica capacitor, R4 is the 55.4, small capital R4, and small R4 is zero point 0.5 ohm. This is the resistance with the capacitance. And then at balance condition, we know that these two arms, and so it will be small R1 plus j omega L1. This is impedance, and by R3, this one will be equals to this R2 by small R4 plus capital R4, and then for C it is minus j by omega C4. And then here you multiply it, and we got this expression. Now you equate the real and imaginary part. What will get? Small r1 r4 plus small r1 capital R4 L1 by C4 will be equals to R2 R3. And if we equate the imaginary part, it will be omega L1 R4 plus omega L1 small r4 will be equals to small r1 plus by omega C4. Now 1 and 2, if you see that here, what are the unknown? Unknown is the capital N1 and small r1, and you see that the r4 is known, and r2 r3 is also known. Here omega is known, L1 is also unknown, and r4 is known, and you see that here r1 is also unknown. So you have two algebraic equations where two unknowns are there. There are two unknowns, and you see that there are two equations, so this can be solved. And one thing you note it that the EMF of V is not so important. That is what it is not mentioned here. It is also important. It is only important that you need to limit this E so that uh, there is no the power dissipation is under control and no damage of the circuit component. So from here you see that L1 will be equals to this. From these two equations, we can solve it. So L1 will be equals to this. And if you substitute all the values, you will get 0.43 Henry. And small r1 will be equals to this. If you solve this, and if you substitute all the value, you will see that the capacitance, the inductance resistance will be this 57.8 ohm. This is the way you could solve it. It's very simple. Maybe the solution of these two equations is little tedious. Otherwise, it is very simple and straightforward. So this is all about one example. Okay. So now tell me if you have any query, because we end the inductance measurement using bridge circuit. Okay. So as you don't have any query, so let's proceed further. So now we'll move to the second part of this section, which is the measurement of capacitance with the help of bridge circuit. Other way also capacitance can be measured, but here the bridge circuit we are reading. So here the measurement of capacitance with the help of bridge circuit. So if you see the left hand side figure, this if there is a capacitance C and it is a real capacitance, always the capacitance will be associated with a pure capacitance, which is mentioned as a C ideal, and associated with resistance in series. Okay, so which is ESR. Okay, or it is written as capital R. Now there is a few things. So the voltage diagram is important. You see the diagram. The VR will be if the VR means the resistance is on the uh, horizontal line, and then VC will be equals to minus 90 degree. That is what is there. Now if you see that DF means dissipation factor. That means how much dissipation will be happening. That will be ratio in between the resistance and the capacitance. So you see that the power loss in the resistance will be I square. If I current is passing through it, the power loss of the in the resistance will be I square R. And if the I current is passing through capacitance, the power loss will be I square XC. So I square will cancel out. So it will be R by 1 by omega C. So it will be omega CR. So dissipation factor, which is also very important, will be omega CR. So dissipation factor will be omega CR, that you have to note it. Now another important thing is that tan delta. So this angle, dissipation angle, also very popularly known as the delta angle. So we can call that it is a delta angle, no problem, because this notation is very fixed. Nobody mentioned this angle with any other symbol. So if you see what is the angle, that will be the voltage between VR and VC. So if you see the tan delta, the voltage triangle diagram, if you see, if it is a tan delta, so you will see that the VR by VC, so VR will be IR and VC will be IXC. So IR and II will cancel out. So R by 1 by omega C. So omega CR. So this tan delta is also omega CR. So here you see that the tan delta, that means tangent of the dissipation factor, angle delta will be same as the dissipation factor omega CR, same expression. Now if you see here from the triangle of the impedance diagram, so here if you see that, if you see that R will be in the horizontal axis, then the j omega jxc, or means j by omega c, or or minus jxc. So that will be 90 degree downwards, and the impedance Z will be the angle delta with that. So you know that impedance will be that will be R square plus this into square root, that also you know. So these three things are very important: tan delta, voltage triangle diagram, and dissipation factor. So with these three things, it will be coming repeatedly. That's what before measurement of capacitance it is mentioned, and then we'll go to the next bridge. So now if you see, another thing is that the quality factor Q. So what is Q? Q is the I square XC by I square R. So XC by R. Now if you see, is there any relationship between Q and the tan delta? You see there is a relationship. So Q is XC by R. So if you, XC means 1 by omega C, so Q will be 1 by omega CR. So will be equals to 1 by DF. That means 1 by dissipation factor will be equals to 1 by tan delta. So here if you see that the, if Q is means quality factor is high, that means high capacity, high quality factor, high Q factor will thus have a low values of dissipation factor. So if dissipation factor is low, tan delta will be low and Q will be high. So less loss will happen. So quality factor will increase if the loss is less. Less loss is happening. Now let's come to the bridges which will be used. So let's come to the bridges which will be used. Let's come to the bridge which will be used to measure the capacity. So first bridge what we will read is the D30 bridge. Okay, let's see if anybody has anything. Okay. So the first thing we'll read is the D30 bridge. So here if you see that again it is the 4 arms, no extra arms are here. So if you see the first term is capacitance C1, second terms BD will be the variable resistance, AC will be another capacitance, and if you see that detector is there between B and C, and fourth term will be another variable resistance R4. So if you see that here there are two variable resistance R3 and R4, and if you see the phasor diagram, this is also very simple. If you see that I1 and I2 will be on the horizontal line, and V1 and V2 will be on the below 90 degree, which is V1 is 1 by I by omega C1, so it will be I by I2 by omega C2, and V will be the. So now if you see at the balance condition, very simple, it is 1 by omega JC1, J omega C1 by R3. R3 will be equals to this 1 by omega C2 by R4. So if you multiply this, we'll get C1 will be equals to C2 R4 by R3. So here see that the unknown is on the AB. So unknown will be C1, and C1 can be calculated very easily with the help of C2, R4 and R3. So you have to achieve the balance condition by varying R4 and R3, and by means of that you will get the C1 value. If you know the C2, obviously you will know the C2. So the advantage of DSATI bridge is its simplicity. The advantage of DSATI bridge is simplicity. It's very simple bridge. However, this advantage may be nullified by impurities creeping in the measurement. That means if the capacitors are known from are associated with the dielectric loss means the tan delta. Okay, so if it is associated with the dielectric loss, this method is not suited. So if the capacitance are made up with the dielectric material, so dielectric loss will come into picture, and then it will be not suited or not very good. But if the capacitance are air capacitance, so dielectric loss is very less. So for those types of capacitance, this bridge can be used very easily, and you will get the very good results. Okay. Now, so the last thing we said that if it is a dielectric capacitors, it is very difficult to achieve, very difficult to get the accurate result. So we need to modify the DSATI bridge. Now you see that here we modified the DSATI bridge. How it is modified? You see that the AB arms will be C1, and now we are considering the capacitance associated with the R. R means if there is a dielectric, then the resistance will come, dielectric loss will come. Earlier we considered the capacitance is not coming with, it is a pure capacitance, it's not coming with the resistance R. But here, and that's what we mentioned, that if dielectric loss is very less, that means tan delta is tends to 0, then it is very beautiful. But if you have a dielectric capacitor, the dielectric material will be associated with it. Due to dielectric material, resistance will come, and due to that you have to consider the resistance, and that method will be not very good. So you need to modify that method. So that is what its modified DSATI bridge is coming, and here you see that capacitance C1 is associated with the small r1, and it is associated with the capital R1 is the resistance, and the capacitance resistance will be small r1, that is mentioned in the arm AB. Now you see the AC arm R2 is there definitely, but you have a capacitance C2, and there is another small resistance with the dielectric resistance is small r2, and arm BD and arm CD are not changed. So you see here in the modified DSATI bridge we consider there is a dielectric capacitance and a dielectric capacitor, and we consider the resistance associated with it, that small r1 and small r2. So now you see that here is the phasor diagram. So if you see that I1 R1 I2 R2 I2 capital R2 I1 capital R1 all are in the same line, that is the line with I1 I2, and the capacitance line is 1 by omega C1, that is the perpendicular down. Delta 1 you see as the uh, dissipation factor, or the this tan delta angle, and then delta 1 delta 2 you see, and from there you see, and then ultimately V is coming on the with the I2 R4 and this one. So you could validate the phasor diagram whatever is drawn here. Now here if you see that balance condition what is being achieved, so it is capital R1 plus small r1 plus 1 by j omega c1. Here you see 1 by j omega c1 by R3. R3 is unaltered. Now here you see instead of only 1 by j omega c2, R2 plus small r2 is also coming. That is also included. So if you multiply it, you will get a single uh, equation, and then you need to equate the real and imaginary parts. So if you equate the real and imaginary part, what you will get? You will get that the C1 will be equals to C2 into R4 by R3. That equation is same. So, and if you see that, so C1 will be equals to C2 into R4 by R3, and here you see that C1 will be equals to R2 plus small r2 by R1 plus small r1 equals to R4 by R3. So C1 will be equals to C2 into R4 by R3. So here another things we need to know, that dissipation factor. If you know the dissipation factor, then only you can calculate the smaller one or two. So dissipation factor of the capacitance are defined. That's what we defined here. Tan delta 1 will be equals to I1 small r1 by I1 by omega C1. I1 will cancel out. We have seen it earlier. So it will be omega C1 small r1. And dissipation factor of capacitor 2 D2 will be equal to 10 delta 2 will be omega C2 R2. Now from the equation C1 by C2 equals to R2 plus small r2 by capital R1 by small r1, this equation, first equation. So from here we could see that, C2, and we multiply it, and then we multiply it. So we got C2 R2 capital R2 uh, small r2 minus C1 R1 small r1 equals to C1 capital R1 minus C2 capital R2, and then here C2 R2, we what we do. So we subtract d2 minus d1, whatever we get, omega c1 r1 minus c2 r2. So here there is a problem, just wait. This last term is wrong. This will also be multiplied by omega, because this equation is multiplied by omega. So here omega will come. So this expression is wrong. Omega will come. So it will be omega c2 small r2 minus omega c1 small r1 will be equals to omega c1 capital R1 minus omega c2 capital R2. Now, if you see what will be the difference between means d1 minus d2 or d2 minus d1, that will be omega c1 r1 minus omega c2 r2, which is on the right hand side. So we can write d2 minus d1 will be equals to omega c2 r2 minus omega c1 r1. We can take out omega c2. So it will come that small r2 minus r1, and that can be substituted, and then we will get r1 r4 r3 by minus r2. So from here, if you see that the dissipation factor with the help of R1, R4, R3, R2, we could know that, and this one, okay. So, and C2 is also known. So we could know that the difference between the dissipation factor, that means D2 minus D1, but the exact dissipation factor is for the both, it is not possible to know, because the number of equations are less, but we could somehow find out that what will be the difference between the two different dissipation factor of the two capacitors. Okay. So now next come to the shearing bridge. So in shearing bridge, if you see, it has also four arms. So R1, C1 we are considering C2 is the ideal capacitor, and a third arm is the R3, and the CD is the fourth arm, which we consider as the capital R4, and a capacitance parallel to it, which is C4. So our objective is to vary R4 and C4 so that a balance condition is achieved. So now if you see that the this one, so I1 is on the horizon, if you take, so 1 by omega C1 will be on the below. So and then I2, if you see I1 and I2, it's a capacitance. So it will be, I2 will be, is the this V1 equals to V2, that 90 degree. So this phasor diagram could be achieved. So now at the balance condition, if you see that small r1 and capital C1, so small r1 plus 1 by j omega C1 by r3 will be equals to 1 by j omega C2 by r4 by 1 plus j omega C4 r4. So if we multiply both sides, numerator denominator, you will get this expression, and ultimately equating immaterial and imaginary part, you will get r4 r1 minus j r4 omega C1 will be this. And from there, if you get real and imaginary part, you will get small r1 will be r3 C4 by C2, and capital C1 will be equals to C2. So these two expression, you see that from this bridge, ultimately the small r1 and capital C1, which are associated unknown, both can be determined, and dissipation factor can easily be determined by means of omega r4 C4. So you can see that the shearing bridge, it is possible to determine that C1 R1, but in the earlier also, this modified D-static bridge, it is also possible to determine. But the one thing is that here we consider our known C2 is associated with some R2, and that R2, if it is known, Then you see, then also if C2 is known, then and small r2, then also it is possible to calculate. And here also in the sharing bridge, we consider there is no small r2, so only capital C2 is there. So it is very simple to calculate the C1 and small r1 associated resistance by means of these two bridges. It's very simple. So the dissipation factor can also be calculated in terms of other parameters like R4, C4, and omega. So this is all about the measurement of capacitance. Okay. Now let's see if you have any query or anything. Okay, as there is no query, so let's continue. So now what we learned the measurement of inductance, we learned the measurement of capacitance, and then next thing will be the measurement of frequency. So with the help of, so this chapter is a bridge circuit. So with the help of bridge, whatever we could measure, we will discuss it. So next is the measurement of frequency. So here our objective is to measure the frequency. So in earlier cases, you have seen that the excitation voltage V is frequency is very well known, but here the excitation voltage frequency is not known, and our objective is to measure the frequency. So here if you see that there are four arms, it's little bit looking complicated. R3 and R4 are very simple resistance arm, and AB, that means R1 arm, that is R1 and a capacitance in parallel with R1, and AC, the another arm, is a resistance R2 with the capacitance C2. Okay, now here you see that external resistance R1 and R2, they are coupled. That means when you move it, it will be moved together. So that means it's a coupled resistance. Okay, so now here is the phasor diagram. It's a similar thing, no need to explain more. So now if you see that the frequency, so in wine bridge, it's a very popular bridge, wine bridge. So you see that what will be the at the balance condition when there is no current passing through the detector. So you will see that the R1 and C1 are in parallel. So you see R1 by 1 plus j omega C1 R1 by R3, and that will be R2 minus 1 j by omega C2 by R4. That also you could write it. So by multiplying j and then that 2 by 1 plus j omega c2, R2, that can also come. No problem. So now if you calculate it, these two terms will be coming. R3 will go up. So R1, R4 will by 1 plus this will be equals to omega c2 R2. So if you see, this is in series arm AC, and series resistance and capacitance, and arm AB is resistance and capacitance are in parallel. That's why here this term is coming, and here only R2 minus j omega c2 is coming because it is in series. So and then you can multiply the both terms. So we'll get this expression, and again you multiply numerator and denominator like this. So you will get these whole terms, and then if you could write it as a real part, this is real part, this is also real part, and this is imaginary part, and then you could equate the real and imaginary part. So ultimately, if you equate it, so what you will get this one C2 R1 R4 equals to C2 R2 R3 plus C1 R1 R3. And if you equate the imaginary part, so your omega square will be equals to R3 by C1 C2 R1 R2 R3, 1 R3 will cancel out. So that's what we have done. So from here we could write this one. We could write R4 by R3 here. If you divide it by the C2 R1 R1 R3, so you will get R4 by R3, and you will get here R2 by R1, and he will get here C1 by C2. Here C1 by C2. Okay. So this expression is achieved. Now this is the imaginary part. That's what I was telling. And you will get omega square C1, C2, R1, R2, R3 will be equals to R3. That's what is written. R3, R3 will cancel out. Omega will be equals to 1 by C1, C2, R1, R2 square root. And the frequency will be equals to 1 by 2 pi root over C1, C2, R1, R2. Now, if you know C1, C2, R1, R2, and most of the bridges, what is done that R1, R2 are taking same resistance is taken. So, and same way it will slider will move. So it will be the coupled, but it's the identical resistance. So R1, R2 will be equals to R. So that two resistance you no need to add. One resistance with coupled. That means same resistance is taken, circuit element is arranged in such a way like that. So R1, R2 at balance condition, R1, R2 will be equals to R, that we can take. So C1, C2 will be equals to C, and then from the equation, this one we could say F equals to 1 by 2 pi C R. So F equals to 1 by 2 pi RC. That is a very famous equation in Wien bridge. So if you know that capacitance and the resistance, you could easily determine the frequency. So this one way oscillator is a very popular and famous oscillator. So hope you understand it. So now the slider for the resistance R2 and R1 are mechanically coupled. That's what I was telling earlier. So it is, if it is mechanically coupled, that means if you slide it, so R1 will be changing, R2 will be changing, but one single slider. And here we do that R1 equals to R2. We do that criteria. So that is what it is coupled. It means that R1 will be equals to R2. So wide bridge is very frequency sensitive. So thus, unless the supply voltage is purely sinusoidal, so achieving balance may be troublesome. Suppose your supply voltage is not sinusoidal, it's different. If it is if it consists of many sinusoidals or many harmonics, it's very difficult to balance. So you have to give a pure harmonic, pure sinusoidal. Otherwise, it will be achieving balance will be very troublesome, since harmonics may disturb the balance condition. So you have to give a input. So it must have a single harmonics, not more than that. Use of the filter with null detectors in such cases may solve the problems. Okay. So if many harmonics are coming, so there are many harmonics components will come through the null detector. So you can use the filter above the null detector so that it blocks other harmonics, only single harmonics will pass, and then you could achieve the null point. Otherwise, it is very difficult to achieve the null point. Okay, let's see if we have any query on Wien bridge. Okay, you don't have any query on Wien bridge. So we finish here our bridge circuits. So earlier when physical classes were going on, I used to tell that you read the bridge circuit from the books. Um, So, but now as we are going fast because it's a slide, so only, so I cover it on the slide. Later I will send that slide to you. So this slide is well maintained. There will be no problem. So now with in this class we complete our bridge circuits. So you read and you try to solve the problem. It's very simple. One question may come from it. So in the bridge circuit, what we learn? We learn how to measure the inductance. We learn how to measure the capacitance. We learn how to measure the frequency. Okay. So that is what we need to know. So these are the very few popular bridges which we read, and the bridge diagram, phasor diagram, balance condition, how to achieve balance condition. From there, how to determine the inductance and the resistance with it, capacitance and the resistance with it, and the frequency. Okay, so that's what we learn. And if you want to know which book you will follow, Sahani you could follow. Otherwise, very precisely, Helpik Cooper also you can follow. Helpik Cooper, it is written very precisely. One small chapter they give. Okay, so Helpik and Cooper, you can follow that book to read the bridge circuit. Okay, so that's all about the bridge circuit. Now tell me if you have any query. Today I'm not going to start another chapters, but the next day I will start with measurement of resistance that is pending. Okay, we did not learn till now that how the measurement of resistance can be done. It could be the very small resistance, it could be the intermediate resistance, it could be very high resistance. Okay, so how it could be achieved, how this measurement can be achieved, that we'll discuss, and it will take maybe 2 3 classes or maybe 4 classes. And then after that, if these are complete, Then we'll move to the measurement of physical parameters, such as the measurement of flow or measurement of distance, length, okay, measurement of strain, all those things. That also you need to know. So, as because you have one single measurement course, so you need to know most popular way of measuring the physical parameters, electrical as well as the non-electrical parameters, that you need to know. So we'll cover that. There is no issue. So now today we could end here. From tomorrow we'll start. Now you just see your mail tomorrow. If there is class, I'll send the mail, or if there is no class, so I'll send the mail also. So you just keep on watching the mails, and we'll start the new chapter or measurement of resistance. Then we'll learn the cathode oscilloscope. Then we'll go to the measurement of physical parameters, pressure, temperature, all those things quickly. Okay, so that is the plan. So now today we could end here, and you could now leave. You dismiss the class. Thank you for attending the class. And if you have any query, definitely you can ask. So, or now you can leave. Okay, thank you for attending the class, and have a good day.